Good morning. Next is neighboring group mechanism. What is neighboring group mechanism? It is occasionally found with a certain substrate that 1. The rate of reaction is greater than expected, and 2. The configuration at a chiral carbon is retained and not inverted or racemized. Once again, it is occasionally found with a certain substrate that, first one, the rate of reaction is greater than expected. That means the rate of nucleophilic substitution reaction is greater than our expected rate. And second one, the configuration at a chiral carbon is retained and not inverted or racemized. That means we know that the reaction via SN2 is inversion and via SN1 is racemization. But here you can see that the reaction is not undergoing inversion or racemization, but what is happening, the configuration is retained. Now, why this is happening? In these cases, there is usually a group with an unshared pair of electrons beta to the leaving group. In such reactions, we can see that there is a group with the unshared pair of electrons beta to the leaving group. We can see a group with the unshared pair of electrons. Such substrate molecules will give this type of reaction. The mechanism operating in such cases is called neighboring group mechanism, and it consists of two SN2 substitutions, each causing an inversion, so the net result is a retention of configuration. So why there is a retention of configuration? In this type of mechanism, we can see that there is a consecutive SN2 reaction, two SN2 reactions. So what will happen? The first SN2 reaction, there is a inversion of configuration, and if it is undergoing one more SN2 reaction, what will happen? We will get retention configuration. The net result is retention of configuration. In the first step of the reaction, the neighboring group acts as a nucleophile, pushing out the leaving group but still retaining attachment to the molecule. So in the first step, I told you the neighboring group is present in the beta carbon and our leaving group is at the alpha carbon. So what will happen? In the first step, the neighboring group will act as a nucleophile and will attack at the alpha carbon and will push out our leaving group from the alpha carbon, but still it will retain into the molecule. Okay, the neighboring group will remain in the molecule. In the second step, the external nucleophile displaces in the neighboring group by backside attack. Only in the second step only what is coming, the neighboring group. That means our not neighboring group. In the second step only our external nucleophile is attacking again from the backside and will displace the our neighboring group. See the neighboring group mechanism. Look in here. Here is a group Z. C, X, R. Now we have external nucleophile Y minus. Before that, you look at this structure. This is our leaving group, halogen. Here the leaving group is halogen. Halogen attached carbon this is alpha carbon, and this one is beta carbon. In this beta carbon, you can see a group. That group is having unshared pair of electrons. So when there is a group having unshared pair of electron at the beta position, will act as a nucleophile and will attack the alpha carbon from the backside, which will result in the expulsion of the leaving group. That means what we get? We get a structure like, before that, look at it here. Since this attack is from the backside, that means this is SN2 attack. What will happen? There is a inversion of configuration. Therefore, we get a structure like this. Here it is R, and here it is C, and you can see that this is our Z. Z is attacking on this carbon, so here is a bond, and Z is getting a positive charge. And you can see that there is a inversion of configuration, so here it is R and R. Plus what will form? Plus X minus. Okay, X minus. Now, this is the first step. What is that? The group with the unshaded pair of electron is acting as a nucleophile, and there is internal SN2 attack result in the inversion of configuration. This R is coming down. Okay, inversion of configuration, and we get a structure like this. In the second step, this is our external nucleophile. Y minus attacks this carbon from the back side, and at that time what will happen? This bond breaks from carbon and we will go back to Z. So what we get? Again, since there is another SN2 backside attack, again inversion of configuration. So we get here it is R. Now this is again become free and it will completely change to this carbon. Now here you can see that inversion of configuration. Here it is R, and here it is Y. This type of mechanism is known as a neighboring group mechanism. So I think it is clear to you. Now first step is SN2, so inversion of configuration. Second step is also SN2, again inversion. So what will happen? Which will result in the retention of configuration. So you can see that the position from which the leaving group is eliminated, the same position our nucleophile is attaching. So this type of mechanism is known as neighboring group mechanism. Now let us consider some examples for this mechanism. First one is carboxylate group as neighboring group. Carboxylate group as neighboring group. Carboxylate group acts as a neighboring group. Look at here. CH3, CHBr, COOH react with AgOH. Okay. Now here you can see that in AgOH the nucleophile is OH minus, and here it is Ag plus and OH minus. OH minus is our external nucleophile. So before that, look at it here, how this reaction proceeds. Okay, we can write C double bond OH, and this carbon C, here it is H, and here you can see that CH3, and here is Br. Now in the first step, you can see that the lone pair electron present on this oxygen. That means the carboxylate group is this one. The lone pair electron or unshaded pair of electron present on this oxygen. This will attack the alpha carbon from the backside, which will result in the expulsion of Br minus, and we have AgOH. AgOH means Ag plus and OH minus is there. This Ag plus goes with Br minus, so what will be eliminated? Minus AgBr minus AgBr, and you can see that since there is a backside attack, there is a inversion of configuration. Therefore, we get a structure like this. Here it is C, and you can see that here it is OH, and this is joining, OH is joining with this carbon, and inversion of configuration. Therefore, here it is CH3, and here it is H. Clear? And in the next step, our external nucleophile. What is our external nucleophile? OH minus attack this carbon from, sorry, here it is a positive charge because oxygen is having 3 bonds. Here it is OH. Oxygen is having a positive charge. When it is attaching, oxygen is getting a positive charge. Now in the next step, you can see that our external nucleophile attack from the backside, attack from the, okay, we can show like this, or simply you show like this, attack from the backside. What will happen? This bond breaks and it will go back to oxygen, and that means this OH group again becomes free. And since OH minus is attacking from the backside, another SN2, there is again inversion of configuration. So we get a structure like this: C double bond O, OH group becomes free, and here you can see that H comes here, and CH3, and what is coming here? Here it is OH. Here you can see that Br is eliminated, the same position our new nucleophile is coming, and the configuration is retained, retention of configuration. Clear? Now, another second one, halogen group. Halogen acts as a neighboring group. Halogen as neighboring group. Second one, halogen as neighboring group. Halogen is acting as a neighboring group. So look at here, CH3, CHOH, CHBr, CH3, then react with the HBr. Okay, here you can see that Br minus is our external nucleophile. Br minus is our external nucleophile, and here this Br is acting as our neighboring group. That means this OH is our leaving group. How the OH becomes a leaving group? Look at here. In the first step, you can see that HBr means H plus and Br minus. This is our nucleophile. This H plus, the lone pair electron present on this oxygen will abstract this H plus. So what will happen? It will change into, so I am writing here, okay, will change into, what will happen? CH3, CH, this will become OH2 plus. Now it becomes a better leaving group, and you can see that Br, and here it is CH3, Br and CH3. Now we can see that okay, look at here. Okay, in the next step, what is happening in our usual neighboring group mechanism? What is that? The unshaded pair of electron present on the bromine atom will attack on this carbon, which will result in the elimination of water molecules. So what is happening? Minus H2O, and we get a structure like what is that? C. Okay, we can show like this. This H is okay, H, and here it is CH3, this CH3, and here it is C, and here it is H, and here it is CH3, and now you can see that Br, and okay, here it is a positive charge. This will also we can represent. Now you can see that this unshaded pair of electron present on the bromine is attacking on this carbon, then minus H2O, and we get a structure like this. Now in the next step, our external nucleophile Br minus, our external nucleophile will attack on this carbon, okay, look at it here, Br minus, this is our external nucleophile attacking from the back side, and we get a structure like what we get, now that time what will happen, the bond breaks and it will be shifted to this carbon, this bromine is become free, only attached to this carbon, so we get, look at it here, since there is a backside attack, inversion of configuration, that means here it is CH3, and here it is EH, and this bromine can be shown here, Br, this bromine, okay, here you can show, and this carbon, okay, this bromine is free to this carbon, so Br, and here it is H, and here it is CH3. Okay, so this step is clear to you. This is our external nucleophile. This external nucleophile is attacking on this carbon. The bond breaks from this carbon and is shifting to oxygen. Therefore, this part is become free. What is that? A Br, H, no change, CH3. Now here, since here is a backside attack, in configuration is inverted. So the CH3 is here and H is here, and our Br is showing here. This is one possibility. Now you can see that in this case, one more possibility is there. That means, suppose this Br minus, so one is this one, and in the second case, look at it here, this, suppose this Br minus, one possibility is there, then in the second case, this Br minus, same Br minus is attacking on this carbon from the backside, and what will happen? This bond is breaking and it will be shifted to heat. So what will happen? In that case, we get a structure like this. That means Br is free to this carbon. So we get C, here it is H, and here it is CH3, and this bromine is bromine belongs to this carbon. And here you can see that since there is a backside attack, inversion of configuration, so here it will become H, and here it is CH3, here it is CH3, and here it is what is that, Br. Okay. So now you can see that these two structures, so if one is plus and this one is minus, that means these are diastereomers, and equimolar mixture of plus and minus, that means here we get a racemic mixture, because the possibility of the attack of the nucleophile on both the carbon atom, in one case, first case it can attack on this carbon, then you get this diastereomer. When the nucleophile is attacking on this, we get this diastereomers. That means these are racemic mixtures. Next is third one, phenyl group. Phenyl group as a neighboring group. Phenyl group as neighboring group. Example, a phenyl group, okay, H, here it is CH3, okay, and here it is H, here it is CH3, and here it is OTS. What is OTS? OTS is a tosylate ion. OTS means, what is that? Tosylate ion. Tosylate ion. Its structure is here it is CH3, SO2, O minus. This is tosylate ion. Okay. This O minus. This is here. And what is OTS? What is OTS means? O. This O. Then SO2. Then ring CH3. That is OTS. This OTS is a better leaving group. It can immediately leave the substrate molecule. So here it is OTS. Now look at it here. Reacting with CH3COOH, acetic acid. So in acetic acid, what is our nucleophile? CH3CO minus is nucleophile, and here it is H plus. Leave that. So this is our nucleophile and H plus. Now we can see that in this case, this aromatic system, that means this bond breaks from this carbon, and it will be will attack on this carbon, and what will be eliminated? Minus OTS. So this bond breaks from this carbon and will attack on this carbon, which will result in the elimination of TSO O minus. That O minus is joining with H plus. That means what we get, what will be eliminated? This OH. Okay, that means H plus is joining, this H plus is joining with the OTS. So it is only this one. So what you will get? TS OH. This is eliminated. Okay, that is eliminated. And what we get? We get a structure like look at it here, the structure. Okay, here it is H, and here it is CH3. Now change, and here you can see that this bond is like this, and since there is a backside attack, inversion of configuration, and we get here it is CH3, and here it is H. Here it is H. Okay. Now, and of course, this bond is here and this bond is here. Since the bond is breaking from this carbon is getting a positive charge. So it is very clear. The bond breaks from this carbon in the set O minus OTS. This minus OTS is taking this hydrogen and it will change into OH. Leave that. That's a leaving group. Okay. Now look at this structure. Now we can see that. In the next step, the bond breaks from this carbon and it will be shifted to here. So here a positive charge. In the next step, the bond is under, therefore there is a positive charge. So you can show a hybrid structure like this, a positive charge in the ring. So in the positive charge in the ring can be shown like this. Okay, positive charge in the ring can be shown like this. Okay. Because we are getting a positive charge here also you can show the positive charge like this. Now you can see that in the next step, our external nucleophile, what is our external nucleophile? CH3COO minus, CH3CO minus is, okay, this is from this carbon, our leaving group is removed. So first the CH3CO minus can attack on this carbon from the back side. And what will happen? This bond is shifting back. So what we get? We get a structure like this. Okay, here it is. Okay, here it is like this, and of course it is like this. The bond is breaking, and here it is. What is that? Here it is H and H, and here it is CH3, and here you can see that. Since backside it take again inversion of configuration, so here it is H and here it is CH3, and what is coming here? Here it is O CO CH3, O CO CH3. Okay, so when the external nucleophile is attacking on this carbon, here also one more possibility is there. What is that? The external nucleophile can attack the other carbon. Now in the second case, you can see that this external nucleophile is, okay, in the second case, the external nucleophile is attacking on this carbon, and then what will happen? This bond is breaking. Okay, and then what we get? We get the next structure like this. Okay, here it is. Okay, here it is like this, and since this bond is breaking, and this first I am showing this one. Here it is H, and here it is CH3, and here you can see that this one and the backside attack. Therefore, what is happening? Here it is CH3, and here it is H, and what is coming here? O. C double bond O CH3, C double bond O CH3. That means here also we get two diastereomers, one is plus and the other one is minus. That means here also we get a racemic mixture. Okay. Then next is acetoxy group. Acetoxy group as neighboring group. What is that? Acetoxy group as neighboring group. Fourth one, acetoxy group as neighboring group. Okay, look at the example. Here you can see that here is our OTS, our leaving group, and here it is O C double bond O CH3 acetoxy group. Okay. Reaction with CH3COOH. Okay, and that means CH3CO minus and H plus. Okay, now you can see that in the first step, you look at it here, this lone pair electron present on this oxygen will attack on this carbon, which will result in the elimination of OTS minus. Will attach, I will take this H plus, and what you will get TSOH minus. TSOH will be removed. Then we get a structure like this. Here it is like this. Since this is backside attack, the you can see that this dotted bond with inversion, that means you can show with a bold thick bond, and what we get here, it is O and double bond C, and here it is okay, here it is O, and here it is C, and in this one there is a CH3. Of course this oxygen is getting a positive charge. Clear? Now this same structure, it can show a resonance structure like this. Now this double bond is between this carbon and the oxygen, or in the next structure you can show this double bond is between this carbon and this oxygen. So the structure, you can draw the structure like this way also. Here it is O, and here this will become a single bond, but here it will become a double bond, and here it is like this, and here it is now this oxygen is positively charged, and this one. Okay, this way also this can be shown. And now in the next step, you can see that our external nucleophile, what is that external nucleophile, CH3CO minus, is attacking this carbon from the back side. Then what will happen? The bond will break and shift to oxygen. That means this group is becoming free. So we get okay. So we get here it is O. Then what is that? C double bond O, CH3. Okay. Since this bond is breaking and it is shifting back to oxygen, oxygen is getting its lone pair electron, and this group will become free, OCOCH3. And since this is a backside attack, this bond can be shown like this. Okay, and what is attacking here? O, C double bond O, CH3. This is the final product. Clear? And the last one, pi bond. Pi bond as a neighboring group. Fifth one, pi bond as neighboring group. Example. Okay, look at this structure. H, O, T, S, and here is a pi bond reacting with CH3, COOH, CH3CO minus and H plus. Look at here, in this structure, you can see that this pi bond breaks from this carbon, and it will attack on this carbon, which will result in the elimination of OTS minus joined with H plus. So what will TSOH will be eliminated, minus TSOH is eliminated, and we get a structure like this. So we get, okay, here it is H, and you can see that the bond breaks from this carbon and is shifting to here. So here is a bond. Since the bond is breaking from here, there is a positive charge. Clear? And in the next step, our external nucleophile CH3 COO minus attacks this carbon, and that time what will happen? This bond again breaks from this carbon and will shift back. So we get final structure like this. Here it is H, and what is coming here? O, CO, CH3, and here is a double bond. Okay, so this is what is neighboring group mechanism, and thank you.